You know, just about everything we do online, from ordering food to streaming a movie to managing our bank accounts, it's all powered by something called distributed systems. These are the invisible, interconnected networks that basically make our digital world work. But wow, are they complex. So today, let's pull back the curtain and explore the core patterns that keep them from falling apart.
I want you to really think about this for a second. You click buy, you send that important message, you save a file to the cloud. That data, it exists on a computer somewhere. But what if that specific computer, that server, just dies right in that instant? How does the system make sure your information isn't just gone forever, or maybe even worse, left mangled and corrupted? To figure that out, we're going to do something a little different. We're going to follow a single piece of data. Let's call it our little data packet on its journey through the system. By seeing the dangers it faces and the clever tricks used to protect it, we'll uncover the fundamental patterns that make these massive, reliable systems even possible. Okay, so our journey starts with the most basic problem of all. Why not just use one giant, super powerful server for everything? Well, it turns out that even the biggest server has its limits. CPU power, memory, how much data it can send and receive. It's a physical box.
As more and more people try to use that one server, requests start piling up, forming a massive queue. Things get slow, performance tanks, and eventually the whole thing can just grind to a halt. Not to mention, if that one server fails, everything is gone. It's what we call a single point of failure. So the solution is pretty clear. You have to distribute the work and the data across many servers. This gives you parallel processing, and it's really the very first step toward building a system that can actually survive the real world.
All right, so our data now lives on one server out of many. But this actually introduces a new kind of danger. What happens if that server crashes right in the middle of doing something important? This is the first life or death moment for our little data packet.
Let's imagine a really simple inventory transfer. The system needs to do two things: subtract 40 widgets from warehouse A and add 40 widgets to warehouse B. But what if it subtracts the 40 widgets from A and then boom, the server crashes before it can add them to B? Those 40 widgets have just vanished into thin air. The data is now inconsistent, and in the real world, that could mean lost money, messed up orders, you name it.
So the goal here is to make this whole operation atomic, meaning either it all succeeds or none of it does. The brilliant solution for this is a pattern called the write-ahead log, or WAL. Just think of it like a safety journal or a ship's log. Before the system even thinks about touching the real data files, it first writes down exactly what it's about to do in this special log.
And this process is what guarantees safety. First, the intention, move 40 widgets from A to B, gets written down in the log. Only after that's securely saved does the system start changing the actual data files. Now, if the server crashes halfway through, it doesn't matter. When it reboots, the first thing it does is read the log. It'll see that unfinished job and simply replay it, making sure the widgets get added to warehouse B. The data is consistent, our packet is safe.
Okay, so our data packet is now safe from a single server crashing. Awesome. But to be truly fault-tolerant, we can't just have one copy of our data. We need to replicate it across multiple servers. And this creates a whole new tricky problem for our packet's journey. If there are copies everywhere, who's in charge? Which copy is the real official source of truth?
This right here is a classic distributed systems nightmare. It's called split brain. And it's exactly what it sounds like. If two different servers both think they're the leader, they could start accepting different updates from users. One server might tell you your bank balance is $100, while another one says it's $50. It's absolute chaos.
The solution to this is a pattern called leader and followers. It's pretty intuitive. The servers basically hold an election, and one of them is chosen to be the leader. Now, this leader is the only one allowed to handle any incoming changes or writes. It records the change, and then it's responsible for telling all the other servers, the followers, to make that same exact change. This ensures there's always a single, ordered source of truth. But networks are messy. What happens if an old leader gets temporarily disconnected from everyone else? While it's offline, the other servers notice it's gone and, correctly, elect a new leader. But then, the old leader reconnects. It has no idea it's been fired. It might just start accepting writes again, completely unaware that its information is now stale and outdated. To solve this zombie leader problem, systems use a really neat pattern called a generation clock. It's just a simple counter that goes up by 1 every time a new leader is elected. So the first leader is from generation 1. The next one is from generation 2, and so on. Now, if that old leader from Generation 1 suddenly reappears and tries to issue a command, the other servers will see its outdated number and just reject it. Simple, elegant, and the problem is solved.
So our leader is firmly in charge, and it's protected from any old ghosts. But this raises a new question for our data packet. When the leader gets a new update, how does it know that the change has been safely saved on enough of the followers before it tells the user, yep, we got it, it's safe?
This is where the idea of a majority quorum comes in. It's basically a democratic rule for data. A decision is only considered final and official if more than half of the servers agree on it. So the leader sends the new update to all of its followers, and then it just waits. It will not consider that data committed or permanent until it gets a thumbs up from a majority of them.
Let's look at this 5-server cluster, for example. The leader needs to hear back from at least 2 followers. Once it has those 2 ayes, plus its own vote, that makes 3, a majority of 5. At that point, the data is guaranteed to survive even if a minority of the servers fail, because that information will always exist on the remaining, healthy majority.
To keep track of all this, the leader uses something called a high watermark. You can think of it as a pointer in its log. This pointer marks the last update that was successfully confirmed by a quorum. It's like the final safety gate for our data packet. And here's the crucial part. Clients, the users, are only allowed to see data that is below this mark. This ensures that no one ever reads information that isn't absolutely, positively guaranteed to be permanent. At this point, our little data packet is incredibly resilient. It can survive crashes, leadership confusion, all sorts of trouble. But what happens when the total amount of data just becomes enormous, way too big to fit on any single group of servers?
The final key pattern we'll look at is partitioning, which you might also hear called sharding. The idea is, instead of trying to replicate one gigantic database, we just chop it up. We split the data into smaller, more manageable pieces. Each of these partitions is essentially its own little mini database with its own leader and followers, and it's only responsible for a small slice of the total data.
So how does your app find the right piece of data in this massive system? Well, with an approach called fixed partitions, it's actually just a simple math problem. The client takes the data's key, like your username for instance, runs it through a quick calculation, and the result points directly to the exact partition that holds your data. It is an unbelievably efficient way to let systems scale out to handle millions or even billions of users. So, we followed our data packet through server crashes, leadership crises, and massive scaling challenges. We've seen how all these different patterns, the write-ahead log, quorums, partitioning, they all work together, each one solving a very specific problem to create a reliable, resilient whole.
And look, these are not just abstract, theoretical ideas. As the foreword to the book we're drawing from says, these patterns are like composable Lego blocks. The write-ahead log, leader election, quorums, partitioning. These are the actual building blocks behind the banking apps, the cloud storage, and the streaming services that you and I use every single day. They're what make our digital world dependable.
What's more, these patterns create a shared language. When engineers talk about building a system using a replicated log with quorum commits, they aren't just using jargon. They're using a powerful shorthand that's built on decades of trial and error. It allows them to construct these unbelievably complex systems without having to reinvent the wheel from scratch every single time.
From the limits of a single server all the way to a globally distributed fault-tolerant network, these patterns are really a testament to our ability to solve incredibly hard problems. They form the very foundation of modern technology. But of course, technology never stands still, which really makes you wonder, what challenges are waiting for us just over the horizon, and what new, ingenious patterns will we need to invent to solve them? Thanks for joining me on this journey.